Now let's get on to looking at the stack. What is the stack and why do we need it? Well, look, let's have a look and we'll see how we were able to jump between one section of the code to another section of the code. And we did this back in, I think it was video number 9 it is. And if you go in about 5 minutes or 5 minutes 30 into that video, you can have a little look and we can see that we were able to set up a loop so we could jump to one position of the code and then we could jump to another position and then another position, and we were able to jump around about the code using the jump commands. So let's have a reminder of that now. So you can see that we set up the loops 1, 2, 3 and 4. Now we're going to jump through those individual loops. So first of all we go through the pass 1 of the assembly and then we're going to move on to the second pass, and that's it jumping through those loops now. So again we can run that once more just to show you it, and we can jump through the looping structure. So that's a reminder of what we did back in video 9. If you're unsure, you can always go back to that video and have a look. Now, the problem that we have with this setup is that if we were to think about the jump as in jumping into a little subroutine, then of course we can always return from that subroutine using another jump, and we just have to tell it where to jump back to. Now, we could also set it up if we were to jump from one subroutine into another. But let's say, for instance, we were then to jump from that subroutine into another one. Or let's say we get to the second subroutine and then we jumped into a third subroutine. And we take the third subroutine and jump into a fourth subroutine. And we could continually jump into subsequent subroutines from other subroutines. But then we would have to keep track of the return addresses so that we could get back to the previous subroutine and then back to the one before that and the one before that. Now, we are not going to do that just using a jump command. We're going to do that using something called the stack. Now, you can gather from what I've talked about so far what a stack is going to be. So I'll explain this in words and then we'll have a look at a little graphic. So really what we want to do is we want to jump to a certain part of the program. So we want to jump to a subroutine. Now, when we jump to the subroutine, what we actually want to do is we want to take a note of the return address. So the return address is going to be just the address after the initial jump. And we can take a copy of that and we can put it somewhere in memory. And then let's say we were to go to that subroutine, and let's say we were to call another subroutine. Now when we call that other subroutine, again we take a copy of the next address after the jump, and again we put it in the stack, but we put it in the next address available in the stack. And we can continually do that. Now, in order to return from the subroutines, what we can do is we can use a return command. Now, when we use the return command, the opposite thing happens. In the return command, we go to the stack, to the top of the stack, and we pull out the return address. So it means we can jump back to the next address in the previous subroutine. And again, if we want to jump back to the subroutine before that, we can go subtract 1 off of the stack, so we go down to the next value in the stack and we can pull that value off, and it takes us back to the previous subroutine. So in doing that, we have a method of saving all of our return addresses, and it allows us to call subroutines from within subroutines from within subroutines. So that's one of the functions of the stack. Now, the stack's quite a useful thing to have, because we don't just use it for the subroutine call and returns. We can also use it to store values. So for example, if we wanted to use registers R0, 1, 2, 3, 4 and 5 to do something, but we don't have enough registers. So what we can do is we can save the values of registers 1, 2, 3, 4 and 5 and any other register, and we can save it in the stack. So we can take those values and just pop them, what we call popping them into the stack. We can push them into the stack. And then we can work using our registers, doing what we have to do. And when we're finished doing what we have to do, we save a value to memory. And then we can go and we can pull all of the values off of the stack and put it back into the registers. So this is a nice, neat little way of organizing our information. And it's a really useful and a basic part of the computer organization. So that's me described it in words. If you're still a little unsure, we'll go ahead and we'll have a look at this image here and I'll talk through in more detail. Now, before we go to implement the stack, let's make sure that we know exactly how it's going to work. Now, I have a representation here of our memory. Now, we know we've got 16 bits, so we've got 2 to the power of 16, which is 65,536 possible memory locations. Now, we've talked about how we were going to map some of these memory locations already. Half of them were going to be in ROM, and the other half were going to be in RAM, and a part of the RAM we were also going to use for the I/O as well. So we've already talked a little bit about this, but now what we want to do is we want to use some of the memory for our stack. Now, whenever we go to implement it, we'll show you what values we're going to use for the stack, but really what we want to know first of all is just where the stack begins. So we're going to pick out a memory location for the stack, but right now we're not really bothered. We'll just pick out any memory location just to show you it working. So if you think about this as our full memory allocation, and let's imagine that we start off at the position 0. I'll get rid of that actually, and I'll put a different colour. Let's say we start off at the first position, which is 0, 0, 0, 0. Now, these are actually in hex, okay? So this actually represents 16 bits. So that's our very first memory location, all zeros. Now, the very bottom here would be the final memory location, which would be our F, 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 okay? Now, what we could do is, let's say for instance at the moment, the way I've done it is I've defined this, or a similar way that I've done it is I've defined the bottom here as the start of the stack. Okay, now what we're going to do is we're going to have to take a note of what position in the stack we're going to be, because for example, if we were going to say put a value in the stack here, and then we were going to put a value here, then here and here, and so on and so forth, then we need to know where we are at each point along the line, because we're going to have to say take a value off and take a value off, and then put a value on, and then off, say off, off, off. And each time that we do this movement of putting values onto the stack and taking values off of the stack, we're going to have to take a note of exactly where we are. So that is, we're going to have a little register that registers our position within the stack, and I've represented that up here, and we're going to have this new register which is going to be called the stack pointer register. So that points to the position in the stack that we're using at the moment. Now, we're also going to have a few commands here. So first of all, we're going to talk through our jump to subroutine and also our return from subroutine. because these were the things that kind of motivated the usage for our stack. Now, the jump to subroutine is going to be different from the normal jump command. So in the normal jump command, we're going to take the address that we want to go to, and that address goes into the instruction address register, so that the next instruction that comes along, it just goes and it points to that new address, and we start working from there. So the jump command is quite straightforward. But the jump to subroutine is different. The jump to subroutine is a special jump command that we're going to use, which allows us to keep a track of the return addresses within the stack. So the normal jump just doesn't do that. So in this instance here, if we have a jump to subroutine, now the way I've set it out, and I've just realised that I could have done it a little bit better, but it doesn't matter. I'll explain this just now. Now, the jump to subroutine here, what we do is we want to make sure that we can take a note of the return address within the stack. So what we do is, in this instance, I subtract 1 off of the stack. So in here, we can see that the stack sits at pointing at FFFF. So what I do is I subtract 1 off of the stack. So now the stack pointer points at FFFE. So this gives us a free available place within the stack. So at this point here, I take a copy of the return address. So let's say the return address is just something, what could be 124D. Okay, again, it's a hex value, so it represents a 16-bit return address. So in effect, that's us. We're now able to go to the jump to subroutine, and we can jump into the subroutine because we've got a copy of our return address. Now let's say we go from that subroutine, and within that subroutine we have another jump to subroutine. So again, what happens is we subtract 1 off of the stack pointer. So now the stack pointer points at F, 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 and that's going to be D. And it gives us a spare place to put in another value. So we put in the next return address. So let's say the next return address is 13AD. So we've got a copy of these. So we're now in the second subroutine. Now we could jump to a third subroutine, fourth, fifth, sixth. We can keep jumping into subroutines. But let's say we only do those 2 jumps. And let's say we want to jump from this subroutine back to this subroutine here. Then what we're going to do is we're going to use a new command, and it's going to be the return command. So in the return command, what we do is we go to the top of the stack. So this is the top of the stack here. And we have the return address. So we just pull out this return address and we return to that point, which takes us back to the correct point within the previous subroutine. But after we then do that, we then add 1 onto the stack pointer. So now the stack pointer won't be pointing here to this point here. The stack pointer will be at this point here. Okay, we don't take this value away. It can still be left. All that happens is whenever we then add another value onto the stack, it will just get written over. But the point is that the stack pointer is now sitting here. So the stack pointer register is now sitting at that point, and if I put it in here, it's going to be sitting at point F, 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 E. And let's say we then want to jump to the original subroutine. Then again, we're pointing to the correct place in the stack. We can do the return command. The return command takes this value off, and it allows it then to return back to the original subroutine. But when we do that, we then we add the value 1 onto the stack pointer. So now the stack pointer goes back to its original value, FFFF. So the stack pointer is now FFFF. So we can do this continually with the jump to subroutine and the return in order to allow us to jump between different subroutines from within other subroutines. So that was one of the ways of using the stack. Now, let's say we aren't actually doing that. We aren't jumping to subroutines, but we want to use the stack in order just to store information and retrieve information. Now we can do that using another two commands. Those are going to be the push and the pop. Now the push command pushes values onto the stack, and the pop command pops values off of the stack. Okay, so push onto the stack, pop off of the stack. Now those are going to work the same way as we've seen the kind of jump to subroutine. What's going to happen is, in order to push a value onto the stack, first of all we're going to add one on. So we're going to subtract one off of the stack pointer so it points to a new available location, and then we push a value on. And we can continually doing that. We can then, if we want to push another value in, we subtract one off the stack and we push the next value. And then we subtract one off the stack and put the next value, and subtract one off the stack and put the next value. Now, if we want to pop the values off of the stack, we go to the top of the stack. Remember, we can only ever go to wherever the stack pointer is pointing to, and we always have to keep an eye on where that is, and we have to use it properly. Okay, so we can go to the value in the stack pointer because it will always be pointing to the top of the stack, and we can pop that value off. But remember, when we pop that value off, we have to add one on to the stack pointer, so we come down to this point here. And again, if we want to, we can pop this value off and then add one on. We can pop this value off, we can add one on, we can pop this value off, and we can go back to the stack. Okay, so if we want to call, what would we call this then? The bottom of the stack. So we'll call this the bottom of the stack. Okay, and as we work our way up, we go up towards the top of the stack. So that's the basic idea of the stack, and it's really quite neat because if we had, for example, what we call interrupts, so whenever you're using your computer, you don't just do one thing, you might be doing 3 or 4 different things all at once. So you're going onto the keyboard, something running in the background, you're going on to, you've got a YouTube channel running and then video running, and you're hunting through the internet. So you've got all these things happening at once, and we have things called interrupts, which we'll deal with later on in the course, which really comes in and says to the computer, listen, could you stop doing what you're doing, because there's this other thing that we have to do, and it's got priority. So it will take a copy of the registers one at a time, and it will subtract one off the stack and put a value in, subtract one off, put another value, and so on and so forth. And it will take a copy of all of the relevant register values. And then whenever it goes through the routine that it's been asked to do, and it's got now control again, it will take all of those values and it will pop all of the values off of the stack. That is, it will take the first value in the stack and it will put it back into a register. It will then add one on, and it will go to the next value and take that off and add one on, and so on and so forth until it goes back to where it started. So you can see here that the stack is a very, very versatile and a very important method of organising the transfer of data around your CPU. Now, there are other ways of implementing the stack. The way I've shown you here, and the way we're going to use, is we start at the bottom address here and we subtract the values off and we work our way up here. Now we could have done it the other way around about. We could have started up here and then started working our way down the way. But it doesn't matter as long as you're consistent and you know how your implementation is and you know how it works. But what is really important is that whenever you're pushing values onto the stack, you have to pop them off. And if you lose the order in which you do it, it will just be a bit of a mess. Okay. Now that's enough for this video. In the next video, we'll start implementing this, and we'll see how we create the stack pointer register, and we'll implement the jump to subroutine and return, and also the push and pop. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.